Given a textual description of the overall room style and the rough room layout based on 3D semantic bounding boxes, our method called ControlRoom3D creates diverse and globally plausible 3D room meshes which align well with the room layout. Generating high-quality mesh representations of 3D scenes is essential for creating immersive experiences in AR/VR applications. However, manually synthesizing these 3D environments is a complex task that requires expertise in 3D modeling software such as Blender. Instead, our method does not require any expert knowledge in such powerful but sophisticated software products. A central element of our method is the 3D semantic proxy room, which allows the user to specify semantic bounding boxes and textual descriptions of the desired room style that then serve as a rough outline for the generated room layout. Our key insight is that this 3D representation, when rendered to 2D, provides valuable geometric and semantic information. This information can be used to control powerful 2D generative models. Leveraging this insight, we present technical components to enable coherent and seamless 3D textures and geometry. At the core of our method lies the user-defined 3D semantic proxy room, which acts as a rough outline for the room layout. We use classical rasterization to render semantic segmentation and instance maps, as well as near and far depth maps from the proxy room. We jointly create a comprehensive 360 view of the room that establishes a coherent and seamless style. We first divide the semantic panorama into 8 views. We then equip a latent diffusion model with 2 adapter models. Firstly, a semantic adapter guides the generation towards the specified room layout, while secondly, the depth adapter conditions the generation on the guidance depth map. Finally, correspondence-aware attention modules using homomorphic correspondences between adjacent frames ensure style consistency between neighboring frames. We employ pyramid blending to create the final panoramic image. After generating panoramas, the next step is to transform these 2D textures into a 3D representation by predicting per pixel depth. Naively estimating depth using a standard depth estimator can yield subpar results due to scale ambiguity. However, the proxy room offers valuable geometric information. We optimize the depth predicted by a pre-trained metric depth estimator to fit within its respective bounding boxes. Additionally, we employ SAM to extract pixel-perfect instance masks for each generated instance by prompting it with the bounding box extracted from the instance maps and restrict the bounding box losses to the respective pixels. While the depth alignment loss aligns the frame with the proxy room, it may alter the object's surface significantly while fitting it into its bounding box. To mitigate this, we present a normal preservation loss, which penalizes deviations from the original normals of the frozen depth estimator. We first perform Poisson surface reconstruction, converting the 3D point cloud obtained from the RGBD panorama into watertight mesh representation. We proceed to remove mesh vertices and their adjacent faces if their density falls below a specified threshold. With the cleaned mesh, we further refine the room mesh by iteratively inpainting the scene from various favorable viewpoints. We first inpaint small gaps using traditional Telia inpainting. We then expand the remaining holes through erosion followed by dilation. This modified mask guides the inpainting of the missing areas using a semantic and depth adapter, yielding the final generated RGB frame. We integrate this new content into the mesh using our geometry alignment module, taking special care to align with pre-existing 3D structure by superimposing its rendered depth. We now show qualitative results of our method. ControlRoom3D generates convincing geometries and textures of diverse styles and layouts given a user-defined room layout and a textual style description.